Is it recording now and is it somewhat focused? Okay, excellent. All right, so this is an introduction to mathematics and statistics mathematical modeling. All right, so how many of you have heard of the Pythagorean one-loss theorem? Or one-loss formula? Okay, not too many, excellent. So the idea of the talk is to derive the Pythagorean one-loss formula. I want to observe some of the key ideas and techniques in modeling. So we talked a little bit about Galileo's experiment when he dropped the two spheres from the Tower of Pisa. Does the color matter? No. Which parts really matter? That's what you want to put in your model. We'll see how advanced theory enters in very simple problems. How many of you remember the drowning swimmer problem from calculus? You've got somebody dying in the water, and the lifeguard is trying to reach them in the least possible time. And the path the lifeguard takes is the same path that light takes when it passes from one medium to another. You actually have a very difficult quartic polynomial to solve from a very simple problem of the path the lifeguard takes. So you have possibly seen in your career similar instances where something doesn't seem that bad, but interesting mathematics enters. The other thing which is really nice about the drowning swimmer problem is you're supposed to run at a little bit of an angle. What do you think most lifeguards do? They run straight at the person. For a lot of things, just being close is good enough. And the amount you save by calculating the right angle, it's not worth doing that calculation as the person is drowning. Right? If you want to pre-calculate it, that's fine. But for a lot of things, the amount that you gain is not that much. And we often look for first-order effects. What's the main term? I want to show you opportunities from inefficiencies. So if any of you have read Moneyball or seen the movie, Billy Bean and the Oakland A's were very famous for exploiting people's lack of understanding about how much certain statistics matter. Somebody in the class actually shared recently an article justifying doing an analysis of this, and I'll pass that along. And then the last is, if there's time, I'll talk a little bit about avenues for future research if any of you are interested in stuff like this. All right. So the goal is to find statistics to describe the real world. All right. Anybody know what bridge this is? Yes. Excellent, right? So right here. Anybody know how long the Harvard Bridge is? 620.1 meters. Excellent. Does anybody know another unit of measurement for the Harvard Bridge? Smoot. The smoot. Okay, so this is a very bad image of smoot. Smoot was a pledge at a fraternity at MIT. There's a reason why we don't have fraternities anymore on this campus. Fraternities often did interesting things with their pledges. The brothers were plagued one night with the age-old question, how many smoots does it take to get across the bridge? So they laid Smoot down, marked him, picked him up, laid him down, picked him up, laid him down, and they found out exactly how long the bridge was. It was 364.1 smoots, and I love the plus or minus 1 here in terms of the units of measurements and the accuracy. MIT is famous for terrific units. They also created the Bruno. It's the indentation in cubic centimeters when you drop a grand piano from the 3rd floor onto a sidewalk. They have a whole slew of wonderful units. This does not seem like a great unit. The police in Cambridge did not think it was a great unit, and they had the bridge repainted. Well, that didn't deter the fraternity. They just picked up Smoot again. And this went on and on for a while, and eventually the police said screw it, and they left the markers. And now, we're actually at the point where when there is an accident on the bridge, I didn't include the picture, they have Smoot markings, and they report in the police write-up, or in the Globe when they're doing the report, how many smoots you were from the edge of the bridge when the accident happened. That is now the accepted unit of measurement. We will meet Smoot later at the end of the talk. We talked earlier about these statistics, which is the right way to describe who's in first place. If you go by winning percentage, at this point in the season it was the Yankees. If you go by games back, amazingly it was the Red Sox, because the Red Sox had played more games, even though they had a smaller winning percentage for those games. We want to find good statistics. The Smoot does not seem like a good statistic. Right. So this is, I think, the first time I was the head coach. This was my daughter's t-ball team. The goal is to go from teams like this to a little bit better teams to starting to win championships. And eventually to getting World Series rings. That is a Red Sox World Series ring. I was not allowed to keep it. I will not mention what I offered in exchange for it, but you could probably guess. And you can actually still see Cameron later today. All right. Here are the parameters for the Pythagorean one-loss formula. Really doesn't need that much. The average number of runs you score per game, the average number of runs you allow per game, and then gamma is some constant different for different sports. So you can do this in football, you can do this in basketball, you can do this in hockey. Why do you think baseball is such a better sport than football for this?
Because theoretically you can score infinitely.
So you could score infinitely in baseball, but it's not the infinite scoring that's the reason why baseball is better. You need to know a little bit about the four sports.
So you can't convert defense to offense.
It's not converting defense to offense. Yes.
Far more many games.
Far more many games, right? Now you have me saying far more many, but okay. 162 games in the regular season in baseball. In football, you have 16. You have 1/10 of the size data. Hockey and basketball, it's on the order of 80. So really, when you do stuff like this, the question is always, how much data do I need to know before I'm comfortable? Anybody ever watch the Cutting Edge movies? My daughter likes to skate, so she and I have watched a lot of those. In one of the movies, a hockey player has converted from hockey because he has an eye injury to figure skating. And he's always nervous, and he always throws up before games. But he reassures his partner that, after 3 minutes, I'm always fine in games and I do well. And she goes, you do realize our program is only 2 minutes, 30 seconds long. Well, 30 seconds after we're done, I'll be fine. If you're going to make predictions, how much data do you need? Are you going to have enough data? With baseball, with 162 games, we can be very confident. With football, with 16 games, it's much, much harder. Especially since in football, a lot of teams clinch a playoff berth well before the season ends, and then they're not trying for their last few games. And that has profound impact. All right, so here's the formula. A team's winning percentage, number of wins divided by number of games, is approximately 1 scored to the gamma over 1 scored to the gamma plus 1's allowed to the gamma. What's nice about this is a really simple algebraic formula. This is the 21st century. We don't need really simple algebraic formulas. We have computers that can crunch through this. Any football fans here? All right. Anybody here know the quarterback formula for the quarterback ranking? Know the formula. So there's a long, complicated formula that deals with lots of different parts of the game. But it's designed so if you give me a number of 100, I know that's a good game. 120, that's a great game. 140, oh my God. So for a lot of things, you don't need to see all the details. You don't need to see what's under the hood. You just need to have that nice number at the end of the day. If you have a closed form expression like this, you can ask questions. If I increase my runs by 10% or decrease my runs allowed by 10%, which is going to have more of an impact? It allows you to get a sense of how valuable is a certain player to your team. And it allows you to make good decisions. So it's originally called the PythagWonLoss formula because when Bill James first wrote this down as a way to estimate winning percentages, he used gamma equals 2. So he got 1 scored squared to 1 scored squared plus 1's allowed squared. Sum of squares looks like, where have you seen sum of squares before? The Pythagoras Theorem. Right. This has nothing to do with triangles and right angle geometry. But sum of squares, it's a nice name. The best value now is about 1.82. And so people used to just take this as a numerical observation, that this does a good job. When I was teaching probability at Brown, or mathematical statistics at Brown back in 2004, one of my students brought this up to me and was very curious as to why it worked. And so I then tried to come up with a mathematical model to explain where this comes from. And so I will share that model with you today. We will show why the model is bad in many cases, but similar to the lifeguard running straight for the drowning swimmer, it's good enough to do a pretty good job. All right. So just to get some numbers, in 2009, the Sox were 95 and 67, scored 872, allowed 736, predicted for 93.4. The Yankees were 103 and 59, predicted to be 95. So sometimes people like to use this formula to estimate what value does a manager have. Is the manager able to eke out more wins than you might expect? A few years ago, the Baltimore Orioles made the playoffs primarily because they were like 19-1 in games decided by 1 run. They just did really, really well in a couple of key situations and just eked out the victories. All right. So here are 3 applications. The first is extrapolation. Halfway through the season, you can use this to assess how are you doing relative to how you expect you should be doing theoretically. And if you are underperforming, you might say, I might actually have a chance of making the playoffs. This is not a lost season. And in fact, a couple of years ago, it was a good year. The Yankees started off at 21 and 29. But anybody who did any analysis knew that the Yankees were significantly better than their record indicated. And the Yankees decided not to consider it a lost season. This was, I think, the season they signed Roger Clemens. They made significant moves and did make the playoffs. In other times, you might say, wow, we're 21 and 29. We really should only be 17. And that, we just don't have a good team this year. We should conserve our resources and work on next year. Maybe not trade people from our farm system to try to get that slugger to help us, or that pitcher to help us this current season. Another is evaluation. If you're consistently overperforming or underperforming, you often attribute this to the manager. So when Joe Torre was the manager of the Yankees, he consistently overperformed as the Yankee manager. The last is, one of the nice advantages is this is an easy formula to use, as I mentioned. You can quickly look and see what would be the impact of getting more runs, of allowing fewer runs. You don't necessarily need that in the 21st century, but it's nice when you have a closed form expression. How many of you are econ and something? So for those of you in econ, unfortunately, it is unlikely that you are going to have a nice closed form expression. What do you have to resort to in economics? You often have to resort to simulations. And if you want to see what would be the effect of changing this, then you run a new simulation. And it's not as easy as having a formula where you can then just change one parameter and see what happens. You have to resimulate and resimulate and resimulate. That's expensive. When you have a closed form expression, that's wonderful. So even if the closed form expression is not the truth, if it's close enough to the truth, it's often extremely valuable. All right. So basics of probability, we've done a lot of this before. So the goal is we have some distribution, and we want to try to model it. So one of the big themes in this class is going to be looking at distributions. The more distributions you know, the more chance you have of finding something that models what's going on pretty well and is easy to work with. So the example that we're going to use later, I actually know about this because of nuclear physics. The more things you know, and this is the value of the liberal arts education, the more, wait, that reminds me of. Okay? So we've done this so many times. Probability distribution that's non-negative integrates to 1. The probability I take on a value between A and B is just the area under the curve. Mean, first question we always ask our probability distribution, it's just x, p of x. The variance, how spread out it is, x minus mu squared. And then independence, knowledge of one gives us no information about the other. All right. Anybody ever watch the old Charlie Brown baseball movies? All right, so I see one person was brought up well. You can thank your father or mother. What happens in the Charlie Brown baseball movies?
It's been a while.
It's been a while. Things never go well for Charlie Brown.
Yeah.
As you know from almost anything involving Charlie Brown, sadly. Here are the two key guidelines for modeling. So if you need to model, you want your model to capture the key features of the system, and it should be mathematical, tractable, or solvable. So why do you think I have the sad Charlie Brown here? So I want to capture the key features, and I want it to be tractable and solvable. What do you think the problem is? So what do you think is going to happen to the model as you include more and more features? Do you think it's going to be, yes?
It's going to be less and less tractable.
Yeah, it's going to become less and less tractable. So if you want to be able to get something nice out at the end of the day, your model typically has to be simple. The more bells and whistles you include, the harder it's going to be. So when you model, you have to really decide what is absolutely essential to include, what would be nice to include. All right, so here is my model. One's scored and one's allowed are independent random variables, and they're given by some probability density functions. Okay? Can anybody give me any reason why this is bullshit? Yes.
They're not independent.
Okay, why not?
You're more willing to give up a run if you're up by a lot more to trade for an out.
Yes. So if you have a big lead, you might be willing to give up runs for outs. What if you're down by a lot? What do you think you'll do if you're down by a lot?
Well, runs scored don't matter as much until you reach a certain threshold, so teams are willing to give runs.
Well, right. So if you have a huge lead, you're willing to give up runs to the other team. What if you're the team that's losing? Who are you going to put into pitch? Pitchers. Okay, yes. Bad pitchers. right? You don't want to waste a good pitcher if you're down by a lot. So in fact, 2 nights ago, the Yankees were trailing the Red Sox 14-1 going into the top of the 9th inning. Who did the Yankees put into pitch? Their catcher. He catches the ball a lot, he throws the ball to the pitcher, so he just has to multiply by -1 and he should be fine. He gave up 2 runs and got 3 outs. That's actually not that much worse than the rest of the Yankees had done. They gave up 14 runs in 8 innings, which is almost what he was doing. But what the Yankees were saying is, you know what? We're down 14-1. It's the 9th inning. We don't think we're going to come back. Let's conserve our pitches for the next game. And if we lose the next game, then that's it. And that was a pretty good strategy. My favorite example is Remlinger used to pitch for the Red Sox. And when you come in as a pitcher, the TV stations often tell you what your earned run average is. It's how many runs you allow per 9 innings. But when Remlinger came in, they didn't tell you his earned run average. And the reason was he had given up runs as a Red Sox, he just hadn't gotten anybody out yet. So it's division by 0, and the network didn't have the symbol for plus infinity. So they just did 3 dashes. The Sox were up 10-3. It's the 9th inning. How bad can Remlinger do? Well, he proceeds to give up a grand slam, but he does get the 3 outs, and the Red Sox get the win. He also gets a save from this, but when you have a huge lead, you are willing to play differently. So there are a lot of reasons why they are not going to be independent. But the hope is that a lot of these things will be lower order terms or might balance out. So if I want to calculate the probability I win, there are 2 ways to do it. I can do it as an integral, or I can do it as a sum. So for the sum, let's imagine I score I runs, and I allow j runs, and I want to calculate the probability I score more than I allow. Then it would just be summing over all pairs I and j, where j is less than I. The other possibility is I do it as an integral, and I score x runs and I allow y runs, and I do it over all y less than equal to x. I don't have to do strictly less than because we know the probability that x exactly equals y is 0. Which do you think is a better model for baseball? Discrete or continuous? Discrete. As much as I would love to see the Boston Globe run an article, Red Sox beat Yankees pi to e. You're never going to see that. That said, I'm going to use the continuous case. Why am I going to use the continuous case even though discrete is far better for baseball? Yes?
Because integrals are easier than sums.
Integrals are easier than sums. This is one of the themes of the course. We can integrate somewhat. Sums are much, much harder. So we will do the integration one. So I've mentioned some of the problems with the models. Other issues are, well, what are the densities for runs scored and runs allowed? Can we actually do these integrals? So what they are versus what is a good approximation to what they are is a slightly different question. We're going to try to find good approximations. Here is my first guess for runs scored and allowed in a baseball game, the uniform distribution on the interval 0-10. This is a nice distribution. It's very easy to calculate. It just doesn't describe baseball. Can anybody give me another distribution to try? Yes?
A normal.
A normal. And thankfully, that is the next slide. All right, so we could try a normal distribution. This is mean 4, standard deviation 2. There are 2 issues with this. What's one issue? You can have negative ones. As bad as some teams are, they will not score negative ones. I've only seen once or twice a team with a negative run total, and that's because there's been a computer error on ESPN or something like that. And I've actually taken snapshots because I find it amusing to have a team at -1. But you will not see a team with negative runs. So that's one problem. What's the other problem? It's not a big problem, but yes.
It's probably underestimating the chance of getting high numbers. Because you just told me somebody got 14, right? And that would be
Well, right. So this particular example might be a bad example. But I'm saying there's some fundamental problem with a normal distribution. So one is that it has negative runs. What's the other problem? If you go in the opposite direction, you can score arbitrarily many runs. Well, technically it's possible the Sox could score 1 trillion runs. Not that likely. But the probability that it's assigned to that is so negligible that we don't worry about it. And it's much easier to just allow a distribution to go off to infinity than to actually truncate the distribution and have a finite integral to deal with. So we will allow teams to score a trillion or a quadrillion runs because the probability that will be assigned to that is so low. All right, so this is a bad distribution because it has negative values. Can anybody give me another choice? Gamma? Okay. I think the exponential is a special case of gamma. So I will then say that the slide is okay because it's a special case of what you're saying. So I'm still okay in terms of predicting what students will say in what order. So here's the exponential distribution. This is nice. It doesn't allow negative runs. It decays rapidly at infinity. But the problem is it says the most likely score is the smallest one. So it doesn't do a good job fitting. So what I'm going to do is I'm going to use the 3-parameter Weibull distribution. How many of you have ever seen the Weibull? Okay, excellent. So even though a lot of you have taken stats classes, you haven't seen this one. Weibull is absolutely wonderful. And if you look at it, even though it has 3 parameters, only one of them really matters. So the first parameter is beta. It's always x minus beta. Beta is just translating things. Who here is a basketball fan? All right. Give me a number where you are damn sure that no pro basketball team will score fewer than that many points in the game.
70.
Do you think no team will score fewer than 75 points in the game?
That's happened.
I'm sorry?
It's happened in the past.
That somebody has scored fewer than 75?
Yeah.
Right, so I wouldn't say 75 is a safe point.
Now.
I mean, if you take 40 or 50, you should be very safe. You might want to even go up to 60, 65, maybe even 70 or 75 because the number of times somebody's below 75 is so small, it's just not worth it. But in basketball, you're not going to start off with low scores like 0, 1, 2, 3. So you might want to shift everything down to start at maybe 60. So that's all beta does. All alpha does is it rescales like meters to feet. Right? It's always x minus beta over alpha. So alpha is just a rescaling parameter. The only parameter that really matters is gamma. Gamma gives you the shape. And so when gamma equals 1, then we actually just get the exponential. When gamma equals 2, you basically get x e to the negative x squared. This is something that I saw in physics. And so in fact, when I first did the analysis, I just did those 2 special cases. And then I noticed, oh wait, they fit in a family. And then that gives me a parameter to look at. This should also be looking at you as, oh, please integrate me, right? You've got an x minus beta over alpha to the gamma, and you have that to the gamma minus 1. That's exactly that's the piece you need to integrate. So this looks like it should be tractable. So here's a couple of different shapes. So here, 1, 0, 1 is an exponential, and the other ones are basically one bump distributions. You go up, you come down. Yes?
Always have an area of 1.
So they will always have area of 1, and that's what this constant over here is for. It will give you an area of 1. So places where it occurs, if gamma is less than 1, this is situations of high infant mortality. Gamma greater than 1 means you live to a ripe old age. This is often used to model demands for movies or demands for songs by various artists. How long will you stay on the charts? Lots of things are modeled by the Weibull distribution. It's just good to get this on your radar screen. We've seen the gamma function several times before. It's the generalization of the factorial function. We're going to meet it throughout the semester. And it turns out that the mean and the variance of the Weibull can be computed explicitly in terms of its parameters and values of the gamma function. It's always nice when you have closed form expressions. So if you want to do this, here's the integration. I'm going to just do it really fast. I want to integrate x times blah. I'm going to do the tricks of adding 0 and multiplying by 1, right? These are the best ways to do nothing. So do x minus beta plus beta divided by alpha times alpha. And now if I have beta times the probability distribution, well, the distribution just integrates to 1. So then just get this now. Then I change variables. I let u equal x minus beta to the gamma. And then when the dust settles, everything comes out nicely. So again, in a lecture in class like this, the idea is to just, okay, he just shifts things, does some algebra, not so bad. If you really care, then you go through and you look at it carefully. But it's just standard Calc 1 here. All right. Road space, space on websites is precious. They don't waste space. If they're going to show something, it's got to be important. Team name, that matters. Okay? How many wins and losses you have. Do you need to give the winning percentage? No, you've got it for wins and losses. Okay, but we don't want people to have to be calculating the winning percentages, so it's nice to give that. how far back somebody's, again, it's nice to have that. It's nice to know how teams are doing in their last 10, what their current streak are. That's not interceptions, it's interleague play, record at home, record on the road. And then XWL is the Pythagorean one loss, expected winning percentage. And that's one of the few statistics they choose to give on sites like this. And so the Sox are 37 and 25, predicted to be 36 and 26, not bad. KC 23 and 36, 23 and 36, not bad. All right, I'm going to skip this part over here. We might do this later in the semester. All right, so here is the main result. If you assume teams runs scored and runs allowed are drawn from independent Weibulls with the same parameter gamma, then the probability that you win is basically runs scored minus beta to the gamma over runs scored minus beta to the gamma plus runs allowed minus beta to the gamma. We take beta to be -1/2. And the reason is from binning. So remember how I said I want to use continuous random variables but things are discrete? If my bin is 0 to just less than 1 is the first bin, and then 1 to just less than 2 is the second bin, if you score 1 run, you're right on the boundary of 2 bins. If I have my bins go from -1/2 to 1/2, then 0 is right in the center. And the next bin is from 1/2 to 1.5, 1 is right in the center. Then 1.5 to 2.5, 2 is right in the center. So in terms of doing the data analysis, you want to shift your bins by -1/2, just so that all of your scores are right in the center of the bins, and it's much better in terms of assigning things. So that's why we'll always take beta to be -1/2. All right, so let's prove this. This is going to be multivariable calculus. All right, this is a prereq for the course, but fortunately it's a nice multivariable calculus. It's just going to be 2 one-dimensional integrals. So the first is because we have formulas for the means, we can actually write down the means in terms of our parameters. So I want to calculate the probability that x is greater than y. So I integrate x goes from beta to infinity, y goes from beta to x. All right, well, let's put in what everything is. I'm going to then shift my variables. I'm going to shift everything down by beta. And so now I have this integral to do. And this integral, we said, is really nice to do, because I have this to the gamma minus 1. So we do our u substitution, and we get 1 minus crap. Okay? 1 times this is easy to do, because this is a probability distribution. So when I do 1 times this, I just get 1. And now I get minus the following. So I've got a bunch of factors. I've got this to the gamma minus 1. And then I have an e to the negative x over alpha rs to the gamma, and then an x over ra to the gamma. So I can write this as x to the gamma over alpha to the gamma, where 1 over alpha to the gamma is 1 over alpha rs to the gamma plus 1 over alpha ra to the gamma. It's just introducing a new parameter, so I can write this in a nice form. Who here remembers seeing this somewhere in some class?
It's a circuit?
It's circuit theory. For resistance, right? So when you add resistors in series or parallel, which one is this? Is this parallel?
Yes.
This is the resistance of a circuit where you add things in parallel. You have a new effective resistance of the circuit. Or if you look at center of mass problems in physics, you see this here. This is one of the reasons why I wanted to give this lecture, to show you that these same ideas, these same techniques, these same problems arise again and again and again. Now what's nice is this is looking a lot like a Weibull distribution. What I would want here is I don't want an alpha rs, I want an alpha. And I don't want an alpha rs here, I want an alpha. Not a big deal. I just multiply by alpha to the gamma over alpha to the gamma. And so when I do that, I now get, oh, that's a new Weibull distribution. And its integral will be 1. So notice, I really didn't have to do that much integration. So now I put everything in here, and then when the dust settles, the formula comes out. And we're done. All right. Any questions on the calculus? All right. So I had to choose a season. I chose a season almost at random. Let's do 2004. Okay. Here is a plot of runs scored and runs allowed for the Boston Red Sox. What do you think? Good fit or bad fit? So I'm trying to find the best fit Weibull. Do you think it does a good job? Does one look better than the other? I think the second one looks better than the first. This is where you want to do much more than just visually it looks good. You want to have some tools, some statistics to say, when do you have a good fit? And so there's a lot of stuff called goodness of fit tests. We might do a little bit of that later in the semester. We want to do something stronger than, looks good. All right. Let's look at some other teams in the American League East. So here's going to be how we set things up. So bin K is the kth bin. This is how many times we observe a value in the kth bin of runs scored and runs allowed. This is going to be the area under the Weibull with the parameters. And then we want to find values of the parameters that minimize our error. So we're going to do errors with squares. Why do you think we're going to square things for errors?
They don't cancel out each other?
They don't cancel out. That's one of the reasons. There's another reason why we square things, and we will talk about that later in the semester. Yes?
It sort of magnifies smaller differences.
Right, but that could be a bad thing.
Yeah.
So, yes.
It's nice to deal with mathematically.
It's nice to deal with mathematically. Why is it nice to deal with mathematically? You can do calculus. So if you do absolute values, you lose the techniques of calculus. So we'll do the method of least squares and regression later in the semester. The reason you measure errors with squares is so that you have calculus. The way I phrase it is, if I'm hired as a consultant, I want to use squares. If I'm hiring the consultant, I want them to use absolute values. And so the idea is you want to make this sum of the squares of the differences as small as possible. The smaller it is, the better the fit. And then there's ways to determine how good of a fit it is based on the size. And so you're going back, here is the Red Sox, here's the New York Yankees in 2004. Good fit, bad fit. How does that compare to the Red Sox fit? Better, worse, tough to say. I mean, I think it's definitely better on the runs scored. The runs allowed, maybe similar.
A little bit worse.
A little bit worse. What about the Baltimore Orioles?
Their run scored is out of way.
Yeah, there seems a little bit too many here and a little bit too few here and there. What about the Tampa Bay Devil Rays? And they were the Devil Rays back then. I mean, they may have had a bad record, but they really knew how to do their decay. Who are we missing in the American League East? The Blue Jays. What do you think about the Blue Jays? But they're Canadian, so you have to take into account for the conversion. No, there's no conversion factors. It's actually good that the Blue Jays are bad. And I will explain a little bit more why it's actually good that the Blue Jays are bad. So let's do a little bit of advanced theory. So does everybody agree that if I flip a fair coin 1,000,000 times, I should get about 500,000 heads? Okay, good. So there's no need to do that. Wonderful. If I told you I got 502,018 heads, would that seem reasonable? If I told you I got 482,316 heads, does that seem reasonable? If I told you you got 693,211 heads, does that seem reasonable? The last one seemed to be a bit too much. So the question is, how far away from 500,000 do you think we can be and still be reasonable? And this is where the standard deviation, this is where the variance comes into play. About 95% of the time, we should be within 1,000. So even the first thing I told you was actually ridiculous. The 482,000, also ridiculous. All of them were ridiculous. I'd be shocked with any of them. So here is what we're going to do now. Instead of just flipping a fair coin 1,000,000 times, let's imagine n people independently flip a fair coin 1,000,000 times. If n equals 5, what's the probability that at least one set is not in that range? There's a 22.6% chance that at least one set is outside the range. With 14, which was the number of teams in the American League East back then, the American League back then, it's a 51% chance. By the time you get up to 50, there's a 92% chance. Well, that kind of makes sense. 95% of the time I should be in here. If I do this 100 times, I'd expect 5 times to be out. So I'd be very confident that at least one of them is out. So as I start getting more and more tosses, I expect more and more times somebody's outside the range. The way you should look at this is if the data looks too good, there's a chance the data has been cooked and rigged. Okay? You cannot always trust data. A lot of the work I do is on Benford's law of digit bias, which has applications in terms of detecting fraud. As this is being recorded, I will not talk about what I have talked to the Internal Revenue Service about when I went to their Boston headquarters. All I will say is it involved some of my students here and methods to detect tax fraud. People do not always know how to generate things truly randomly, and you can use this to detect when something has gone on. You can use this for images to detect has somebody modified an image. This is extremely important in the era of terrorism because you can actually hide an image inside another image. And if you know how to unmask it, if people are interested, I'll show you how to do that later. You can actually pull out a hidden message and not have to be doing communications. So we expect occasionally somebody to be a little bit off. So here is the analysis. So the idea is it's called the chi-squared goodness of fit test. The smaller the sum of the squares, the more likely it is that your theory is correct. The larger it is, the less likely it is. So the critical threshold is with 20 degrees of freedom, about 95% of the time you should have a value of 31.41 or less. 99% of the time you should have a value of 37.57. I'm not going to do this part over here as the runs scored and runs allowed independent. I'm going to just focus on runs scored and runs allowed. And if you look, only one value is really significantly bad. Which is that one value? It's the Blue Jays at 41.18. There's something called the Bonferroni Adjustment. How many of you have heard of the Bonferroni Adjustment? So it deals with multiple comparisons, and it's exactly this issue I just mentioned, that when you have so many comparisons, your theory could be correct, but you'd be shocked if you're good every single time. And if you get to inflate the values a bit, so now you get to inflate the value to 41.14 at the 95%. It's 41.18, fine, that's about where it should be. And so the fact that the data is not too good, I actually think is a good indicator that something might be going on here. Real world data should not be perfect. I know there are some schools where professors change the calibration of instruments in labs so that if somebody ends up having a really good lab in terms of their analysis, they know that they've just done the lab at home and made up numbers with error terms. I don't believe they do that here at Williams, but just it would be shocking if it was always very good. All right, as long as it's here, this is just talking about our runs scored and runs allowed statistically independent. So this is actually what got me my connections with Major League Baseball. The senior analyst at one of the teams was curious about this part of my paper. So we talked about how runs scored and runs allowed can't be independent. If you have a huge lead, if you're down by a lot, but there's another reason why they can't be independent. They do something to the same thing across the whole population, but in a given game, specific game, why can't runs scored and runs allowed be independent? And you have to know a little bit about Major League Baseball history and a commissioner who wanted to make sure a terrible catastrophe was never repeated.
There can't end with a tie.
You cannot end in a tie. We do not have enough time to go into why it would be so bad for a baseball game to end in a tie. You just have to accept on faith that this would be a catastrophe. And there is a rule in baseball that you cannot end in a tie. So if necessary, you will have extra innings, and you will keep having extra innings until the game ends. And so there was a great game, the Mother's Day Miracle, years ago for the Red Sox. Whoops, I should not have picked that up. Is it back in focus? Okay. Where the Sox were trailing 5-0 going into the bottom of the ninth inning, and the Sox scored 6 runs, the last 1 or 2 coming from an error. But you know the game can't end in a tie. So for us, the big thing is called structural zero. So I just want to mention this briefly in case anybody has seen stuff like this in stats. Have any of you seen R by C contingency tables? Has anybody seen that? If no one has seen it, I'm not going to make the comments on this, but you just have to adjust your analysis based on the fact that certain comparisons can't happen. This is also done in the hospital business. If you go in for surgery, the hope is that they don't make you worse. Occasionally, yes, they remove the wrong organ or they do this is why they often draw things on people to make it really clear this is the side you're supposed to work on. Okay, it sadly does happen. But the hope is that when you're trying to understand the treatments, it doesn't make you worse. So certain cells should be inaccessible. And that's what got some of the Major League franchises interested in me. So just to briefly summarize, how good of a job does it do? Well, here's the 2004 season, looking at observed wins, predicted wins, observed winning percentage, how many games it's off by. So some teams, people in innings did really well. Some teams, the Yankees, were 13 games above their prediction. The Royals were 10 games below their prediction. On average, you're off by around 4 games a season, which isn't that bad. And if you look at the best values of gamma, the mean is 1.74, the median is 1.76. It's not that far off from the observed value of 1.82. So what I like from this is we're able to find parameters such as the Weibulls are good fits. The runs scored and runs allowed, they're not independent, but they seem to be behaving as if they were statistically independent. We now get that the Pythagorean one-loss formula is a consequence of our model. It's not just a numerical fact like the sun rises. It's now, we have some reason to believe why this is true. And we also have some sense now of how valuable runs are to winning. And then, how many of you have seen the method of maximum likelihood? So if you've seen that, you can do that rather than doing method of least squares. You get similar values for that. There's a lot of other questions you could ask. One is a microanalysis. How many of you have ever watched returns in a presidential election? How long does it take for them to call Massachusetts after the polls close? Right away. How long does it take them to call Texas after the polls close? Or California? There are certain states that they can call immediately. They know what's going to happen. Other states, the battleground states, takes a lot longer. You can do the same thing here. You can say, with 7 innings in the book, we're going to call this game for the Red Sox. And depending on what your threshold is, you can say, look, these are just going to be garbage innings. Hell, the Yankees are putting in their catcher. We don't want to give the Red Sox offense credit for 2 runs, because the Yankees are now using their catcher. You can actually do a microanalysis. I had one of my students do this at Williams as his thesis. It actually doesn't improve things that much. For all the work you do, it doesn't really help. You can take into account ballpark effects. Doesn't really help that much, which is nice. It's nice that the simple model does such a good job. You can do things for other sports. You can try to find out that other probability distributions that might do a better job that can still lead to integrals that can be done in closed form. I've done linear combinations of Weibulls, which is not too bad. As I mentioned, it gives you valuing of runs. The last, I just want to end with seizing opportunities, because you never know where they will lead. So I've mentioned that several students are working on various consulting projects with me. If you are interested, I've been talking with people in North Adams in the area who have projects that are accessible to students. Email me if you're interested, because we're about to get to the point where I need more students for stuff like this. So we mentioned Smoot earlier. This was the poor fraternity person who was used as a unit of measurement. Does anybody know what happened to Smoot and how this impacted his life? You cannot make this stuff up. This is the oldest Smoot, chairman of the American National Standards Institute. Well, I don't like to brag, but I am a unit of measurement. Part of this is you do want to be able to connect with people. I have no idea how he got this position. I'm sure he's extremely well qualified. But I wouldn't be surprised if at some point in his career it actually became beneficial that he was the object of the fraternity break. This is one of the reasons to go to a school like Williams. This is one of the reasons why I am willing to spend an entire class on something like this, because it's not just the math that I want to talk to you about, it's how do you communicate with people, how do you make the connections. You've got to talk to people. You've got to convince someone to give you the job, to give you the chance, to go with your recommendation. How do you interact with them? That's extremely important. And so when I got the call or the email from somebody who was a senior quant person, I didn't know who this was. What do you do when you get an email from somebody and you don't know who they are? You look them up. And I quickly Googled them. Oh, senior quant person, okay. And that was a wonderful opportunity. And because of that, my students and I have been able to do a lot of things with Major League Baseball over the years. All right, any questions on this?